The universe is not the quiet, orderly place it might seem when we gaze up at a calm night sky. Hidden beneath that serene expanse are echoes of chaos, ancient, violent events so powerful they still ripple through space today, shaping everything from the birth of stars to the very fabric of reality itself. Think of it like this: the cosmos has a memory, a shadow of its turbulent past written in the light of distant galaxies, the orbits of planets, and even the atoms that make up our bodies. And what we're about to uncover are the stories behind 32 of these cataclysms, events so colossal their aftermath still echoes across billions of years. Picture a time when galaxies collided in spectacular crashes, sending shockwaves through the void. Envision supernovae so bright they outshone entire galaxies, their explosions seeding the universe with the building blocks of life. These weren't just fleeting moments, they were turning points, cosmic disasters that set the stage for everything that followed. The iron in your blood, the gold in your jewelry, even the calcium in your bones, they were forged in the heart of these unimaginable explosions, scattered across space by forces beyond comprehension. This isn't just a journey through space, it's a voyage through time itself. We'll trace the footsteps of these ancient catastrophes, uncovering how they shaped the Milky Way, influenced the birth of our solar system, and perhaps even played a role in the emergence of life. Some of these events are so distant that their light is only now reaching us, carrying secrets from an era long gone. Others left scars so deep we can still see them etched into the heavens. So buckle up, because by the time we're done, you'll never look at the night sky the same way again. The universe is far from silent. It's telling us a story. And it's time we listened. The first and greatest of these cosmic cataclysms wasn't just an event, it was the event. The Big Bang didn't happen in space because space didn't exist yet. It was the moment reality itself burst into being, a fireball of pure energy expanding faster than light, cooling as it grew, until particles began to form from the chaos. In less than a second, the universe went from smaller than an atom to the size of a galaxy cluster, carrying the seeds of everything we know: stars, planets, even us in its wake. What's astonishing isn't just the scale of that explosion, but how its fingerprints are still visible today. The cosmic microwave background, that faint glow filling the night sky in every direction, is the cooled remnant of that first unimaginable flash. It's like finding the ashes of a fire that burned nearly 14 billion years ago, still warm to the touch, and hidden in that ancient light are tiny fluctuations, ripples in space-time that would one day become galaxies, drawn together by gravity's invisible hand. But here's what really bends the mind: the Big Bang didn't just create matter, it forged the rules of reality itself. The exact balance of forces, gravity's pull, the strength of atomic bonds, even the speed of light, were set in those first fractions of a second. Change any one of them by even a fraction, and stars might never have ignited, planets might never have formed, and life as we know it would be impossible. We're not just products of the universe, we're echoes of its first and most violent breath. After the fireball of the Big Bang faded, the universe plunged into darkness, a cold, empty expanse where not a single star yet shone. For millions of years, space was a silent sea of hydrogen and helium, drifting aimlessly in the void. But then, something extraordinary happened. Gravity began pulling those scattered atoms together, forming dense clouds that grew hotter and hotter until ignition. The first stars erupted into existence, and with them, the cosmos got its first taste of light since creation itself. These weren't just any stars. They were titans, hundreds of times more massive than our sun, burning furiously and living fast. Inside their cores, temperatures soared so high that hydrogen fused not just into helium, but into heavier elements, carbon, oxygen, even iron. This was the universe's first alchemy, transforming primitive gases into the raw materials of planets, oceans, and life. But such brilliance came at a cost. These stars were so massive that they exhausted their fuel in mere millions of years, collapsing under their own weight in catastrophic supernova. When they died, it wasn't a quiet fade. These explosions were so violent they outshone entire galaxies, hurling their newly forged elements across space in shockwaves that stretched for light years. That stardust didn't just vanish, it became the seeds for everything that followed. The iron in your blood, the silicon in the rocks beneath your feet, even the oxygen you're breathing right now, they were all born in the hearts of those first stars, scattered by their deaths like cosmic breadcrumbs. Here's the incredible part. We've actually found traces of these ancient giants. Astronomers have detected faint chemical fingerprints in some of the oldest stars in our galaxy, tiny, dim relics that formed from the ashes of those first supernova. They're like cosmic time capsules, preserving the composition of the universe before planets even existed. Without those pioneering stars, the cosmos would still be a barren wasteland of hydrogen and helium. Their explosions were the universe's first act of recycling, turning destruction into the foundation for everything we know. Long before our solar system even existed, the Milky Way endured a violent encounter that would change its destiny. Imagine two galaxies, each containing hundreds of billions of stars, drifting toward one another in the vast cosmic dark, pulled together by gravity's unrelenting grip. Their collision wasn't a fiery crash like you might picture, but a slow, gravitational dance that stretched across millions of years, warping their shapes and scattering stars like leaves in a storm. This wasn't just a passing event. The impact left scars we can still see today. Look at the Milky Way's outer halo, and you'll find stars moving in strange, looping orbits, remnants of that ancient merger. Some of them even form ghostly rivers of light stellar streams stretching across the sky like cosmic fingerprints. These are the survivors of the smaller galaxy that merged with ours, its stars torn apart but never truly gone. But destruction also brought creation. The collision sent shockwaves through clouds of gas and dust, compressing them until they ignited into brilliant new stars. Many of the stars we see today, including some in our own neighborhood, might owe their existence to that chaotic encounter. It's a reminder that even in the cosmos, chaos isn't just an end, it's a beginning. The Milky Way didn't just survive this collision. It grew stronger, richer, more diverse because of it. And here's the wildest part, it's happening again. Right now, the Milky Way is on a collision course with the Andromeda galaxy, our largest neighbor. Billions of years from now, the two will merge in a spectacle that will reshape the night sky forever. But if history is any guide, even that cataclysm won't be the end. It'll just be the next chapter in an epic story of destruction and rebirth written across the stars. Some stars don't fade quietly into the night. They rage against the darkness with explosions so violent they rewrite the cosmos around them. In the constellation of Carinae, one such star staged a performance that left astronomers speechless. Eta Carinae, a hypergiant so massive it defies imagination, erupted in the 1800s with a force that briefly made it the second brightest object in the night sky, outshone only by Sirius. But this wasn't just a flare-up, it was a cosmic tantrum, a star tearing itself apart and hurling enough material into space to construct 10 suns. What made this eruption so extraordinary wasn't just its scale, but the aftermath. Instead of vanishing, Eta Carinae left behind a glowing, hourglass-shaped nebula. the homunculus nebula expanding outward at speeds topping 2 million miles per hour. Inside those turbulent clouds, astronomers have found traces of everything from common elements like nitrogen to rare metals forged in the star's unstable core. It's like stumbling upon a cosmic crime scene where the debris tells the story of a star's near self-destruction. But here's what's truly chilling: Eta Carinae isn't done. This star is a ticking time bomb, teetering on the edge of a supernova that could light up Earth's sky brighter than the full moon. When, not if it finally explodes, the blast could shower our solar system with enough gamma rays to strip away ozone layers and bathe the planet in ultraviolet radiation. Yet even this looming catastrophe offers a gift. By studying Eta Carinae's tantrums, scientists are unlocking secrets about how massive stars live, die, and sculpt the universe around them. The homunculus nebula isn't just debris, it's a time capsule. The light we see today left the star over 150 years ago, meaning we're watching its violent past unfold in slow motion. Telescopes have even spotted strange, dust-enshrouded knots in the nebula, each one a fossilized chunk of the star's outer layers, frozen mid-explosion. For astronomers, it's like having front-row seats to a stellar breakdown, offering clues about how the universe's heaviest stars seed galaxies with the ingredients for new solar systems, and perhaps even life. What happened to Eta Carinae isn't just history. It's a preview. Across the cosmos, other unstable giants are brewing similar eruptions, and each one could be the next great cosmic light show. The difference this time, we're watching with eyes wide open, ready to decode every flash, every shockwave, every whisper of stardust. The universe doesn't just create cataclysms, it turns them into classrooms. And Eta Carinae is teaching us one explosive lesson at a time. Right now, as you look up at the night sky, two galaxies are racing toward each other at a speed that defies human intuition, 250,000 miles per hour. The Milky Way and Andromeda, locked in a gravitational embrace, are destined to collide in a slow-motion dance that will utterly transform both of them. But here's what's wild: this isn't some distant, abstract event. It's already underway. The first delicate gravitational tendrils of Andromeda have already begun tugging at our galaxy's outer stars, a preview of the cosmic rearrangement to come. When the main event unfolds about 4 billion years from now, it won't be the fiery crash you might imagine. Stars are so far apart that most will glide past one another like ships in an endless ocean. But gravity will warp both galaxies beyond recognition, stretching their spiral arms into long, luminous ribbons. Imagine looking up to see Andromeda filling half the sky, its dust lanes and star clusters glowing brighter with each passing millennium. Over billions of years, the two will whirl around each other, trading stars in a celestial tug of war until they finally merge into a single, colossal galaxy, dubbed Andromeda by astronomers. This collision won't just rearrange the heavens, it'll rewrite the very chemistry of our galactic neighborhood. As gas clouds smash together, they'll ignite waves of new star formation, some so massive they'll burn out in supernova explosions within millions of years. Those explosions, in turn, will seed the merged galaxy with heavy elements, forging the raw materials for new planets and perhaps new life. Our solar system might be flung to the outer edges of this new galaxy, or it could be hurled toward the chaotic core, where starlight from millions of newborn suns would paint our skies in perpetual twilight. The most mind-bending part: this isn't the first time our galaxy has endured such a collision. The Milky Way's history is written in the ghostly trails of stars left behind by smaller galaxies it's already consumed. Each merger left its mark, enriching our galaxy with new stars, new elements, and new cosmic drama. Andromeda's arrival is just the next chapter in that story, a reminder that even galaxies aren't eternal islands, but ever-changing tapestries woven from cataclysm after cataclysm. For now, Andromeda hangs in our sky as a faint smudge of light, a quiet omen of the upheaval to come. But when the merger finally happens, it'll be anything but quiet. It'll be a rebirth, a cosmic phoenix rising from the chaos, sculpting a new galactic home from the ashes of the old. And somewhere in that vastness, our descendants, if humanity endures, will gaze up at a sky utterly transformed, bearing witness to the universe's unending cycle of destruction and creation. Our solar system wasn't born in solitude. It emerged from chaos, sculpted by forces far beyond our infant sun's reach. Roughly 4.6 billion years ago, a vast molecular cloud drifted through a quiet corner of the Milky Way, a cold, dark nursery of gas and dust. Then catastrophe struck. A dying star, perhaps just a few light years away, reached the end of its life in a supernova explosion so powerful it sent shockwaves rippling through the cosmos. When those waves reached our corner of space, they did something extraordinary. They squeezed that dormant cloud like a cosmic fist, triggering its collapse. This wasn't just any collapse. Under the pressure of those shockwaves, pockets of gas grew denser and hotter until ignition. A new star flared to life, our sun. But the supernova's influence didn't stop there. The explosion also peppered the surrounding cloud with heavy elements: oxygen, carbon, iron forged in the dying star's core. These atoms became the building blocks of planets, including the rocky world we now call home. Without that violent stellar death, Earth might never have had the ingredients for oceans, mountains, or even life itself. Evidence of this cataclysm is written in meteorites, ancient space rocks that have remained virtually unchanged since the solar system's birth. Hidden within them are tiny grains of material older than the sun itself, minerals like aluminum-26, an isotope with a radioactive half-life so short it couldn't have formed naturally in our solar system. The only explanation: these exotic atoms were blasted into our neighborhood by a nearby supernova, then frozen in time inside asteroids. It's as if the universe left us a forensic trail, clues etched in stone about the violent origins of our cosmic home. But here's what's even more remarkable. That supernova might have done more than just provide raw materials. Its shockwave could have shaped the entire architecture of our solar system. Some scientists believe the force of the blast compressed the cloud unevenly, explaining why the sun's planets orbit in a flat, disk-like plane rather than a chaotic sprawl. Even Jupiter's massive size might owe something to the explosion's aftermath, as the shockwave's turbulence created dense pockets where gas giants could rapidly grow. Think about that for a moment. The same cataclysm that seeded our world with life's essential elements might also have set the stage for Earth's perfect position, not too close to the sun's scorching heat, not too far from its warming light. A little more force in that shockwave, and our planet might have formed in a harsher orbit. A little less, and the solar system could have remained a loose, disordered collection of debris. Instead, we got a rare cosmic gift, a stable, life-friendly neighborhood, carved by destruction billions of years before the first microbes stirred in Earth's primordial seas. The universe has a way of turning endings into beginnings. That long-dead star didn't just vanish, it became part of us. Every breath you take contains oxygen atoms forged in its final moments. The calcium in your bones, the iron in your blood, even the silicon in the glass on your table, they all trace their lineage back to that cataclysm. So the next time you look up at the sun, remember, its light is only half the story. The true tale begins in darkness with a shockwave from the grave of a star we'll never know, a cosmic spark that set our story in motion. The solar system's early years were anything but peaceful. Long after the planets had formed, a sudden storm of destruction swept through the inner solar system, a chaotic onslaught known as the Late Heavy Bombardment. Imagine a time when the skies above Earth were lit not by the gentle glow of the moon, but by the fiery streaks of countless asteroids and comets, each one a potential world ender. For hundreds of millions of years, these celestial projectiles rained down, carving craters the size of continents and turning the young planets into cosmic battlegrounds. What caused this violent episode? The leading theory points to a gravitational domino effect. As the giant planets Jupiter, Saturn, Uranus, and Neptune drifted into new orbits, their immense gravity kicked swarms of asteroids and comets inward like celestial billiard balls. The result was a solar system under siege, with Earth, Mars, and Venus bearing the brunt of the chaos. The scars of this bombardment are still visible today. Look at the moon through a telescope, and those dark patches you see. The Luna Maria are ancient lava flows that filled basins carved by cataclysmic impacts. Earth, too, would have been scarred, though erosion and plate tectonics have erased most of the evidence. But here's the twist: this period of destruction might have been the key to life itself. Many of those impacting comets were cosmic ice cubes carrying vast amounts of water. When they slammed into Earth, they could have delivered the oceans we know today. Even more tantalizing, some asteroids were rich in organic molecules, the building blocks of life. It's possible that the very compounds that eventually formed DNA hitched a ride on these rogue space rocks, turning a time of devastation into a hidden act of cosmic delivery. The Late Heavy Bombardment wasn't just random violence. It was a sculptor reshaping worlds and setting the stage for life's emergence. Without it, Earth might have remained a dry, barren rock, devoid of the water and chemistry needed to spark biology. And we're not the only planet that bears its fingerprints. Mars, too, shows signs of this ancient pummeling, with vast impact basins that might once have held water, and perhaps even fleeting life. This cataclysm teaches us something profound about the universe. Chaos and creation are often two sides of the same coin. The same forces that battered the young planets also gave them the tools to build something new. The next time you take a sip of water or feel the warmth of the sun, remember, you might owe your existence to a time when the sky was falling and the solar system was remade in fire and ice. 66 million years ago, the sky fell, not in a metaphorical sense, in a very literal, world-ending way. A mountain-sized asteroid, perhaps 6 miles across, slammed into Earth at 45,000 miles per hour, packing the energy of 1 billion nuclear bombs. In an instant, the tranquil Cretaceous world vanished. The impact near what's now Mexico's Yucatan Peninsula didn't just wipe out the dinosaurs, it rewrote the rules of life itself, triggering one of the most dramatic turning points in our planet's history. The first moments of the Chicxulub impact were almost beyond comprehension. As the asteroid struck, it vaporized rock, creating a fireball hotter than the sun's surface. Shockwaves radiated outward, flattening forests thousands of miles away. Tsunamis hundreds of feet high roared across coastlines, while seismic waves rippled through the planet's crust like a bell being struck. But the real devastation came from what followed. The impact hurled billions of tons of dust and sulfur high into the atmosphere, blotting out the sun for months, maybe years. Temperatures plummeted as Earth entered a global winter photosynthesis ground to a halt. Food chains collapsed, and 75% of all species vanished in what we now call the Cretaceous Paleogene extinction. This wasn't just bad luck for the dinosaurs, it was a cosmic reset button. Large, cold-blooded reptiles that had ruled for over 100 million years were suddenly at a disadvantage in this new, darkened world. But small, warm-blooded mammals, creatures that had scurried in the shadows for ages, found their moment. With the dinosaurs gone, these adaptable survivors diversified explosively, filling ecological niches that had been off-limits for eons. Without that asteroid, primates might never have evolved, and humans would never have appeared on the evolutionary stage. Here's what's wild: we've found the crime scene. The Chicxulub crater, buried under half a mile of sediment, was discovered in the 1970s by oil prospectors. Drill cores from the site reveal layers of melted rock, shocked quartz crystals, and iridium, a rare element abundant in asteroids but scarce on Earth's surface. These clues form a forensic trail leading straight back to that fateful day. Even more astonishing, in 2016, scientists drilled into the crater's peak ring and found granite that had been liquefied and reburied within minutes, preserving a snapshot of the impact's unimaginable violence. But the Chicxulub story isn't just about destruction, it's about resilience. Life didn't just survive, it thrived in new ways. Flowering plants, which had been minor players in dinosaur-dominated ecosystems, exploded in diversity after the impact, creating the colorful landscapes we know today. Birds, the last living dinosaurs, adapted to fill the skies, and those tiny mammals, their descendants would eventually walk on two legs, harness fire, and gaze up at the stars, wondering about the very event that made their existence possible. The next time you see a bird outside your window or admire a field of wildflowers, remember, you're looking at the legacy of a catastrophe. The universe doesn't just take, it gives, reshuffling the deck in ways we're only beginning to understand. Chicxulub wasn't an ending. It was the dawn of a new world, one where chance and chaos conspired to make room for creatures like us. And that's the paradox of cosmic cataclysms. Sometimes, the very events that erase one future are the ones that make another possible. On the morning of June 30th, 1908, a blast ripped through the skies over Siberia with such force that it flattened 80 million trees across 800 square miles, yet left no crater. The Tunguska Event remains one of the most puzzling cosmic mysteries of the modern era. At around 7:17 a.m., eyewitnesses described a fireball brighter than the sun streaking across the heavens, followed by a shockwave so powerful it knocked people off their feet hundreds of miles away. Windows shattered in distant villages, seismic stations across Europe registered the vibrations, and night skies glowed strangely as far away as London for days afterward. But when scientists finally reached the remote epicenter years later, they found something baffling: a radial pattern of scorched, flattened trees, but no impact site. The leading theory: a cosmic intruder, likely a stony meteoroid or a fragment of a comet, exploded in midair with the force of 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. At an altitude of 3 to 6 miles, the intense heat and pressure caused the object to disintegrate violently, unleashing a firestorm of superheated gas and shockwaves without ever touching the ground. It's a phenomenon known as an airburst, and Tunguska serves as the most dramatic example in recorded history. What makes this event so chilling isn't just its scale, it's the fact that it happened over an uninhabited region. Had the object arrived just 4 hours later, it could have obliterated a major city like St. Petersburg or Stockholm, rewriting human history in an instant. Even more unsettling, we didn't see it coming. Early 20th century astronomy lacked the technology to detect such objects, a reminder of how vulnerable we remain to similar threats today. Modern simulations suggest the Tunguska object was relatively small, perhaps only 100 to 200 feet wide, tiny compared to the dinosaur-killing Chicxulub asteroid, but still capable of regional devastation. And here's the kicker: NASA estimates there are millions of near-Earth objects in this size range, and we've catalogued less than half of them. A Tunguska-scale airburst could occur every few hundred years, meaning we're statistically overdue for another. Yet there's a silver lining. Tunguska became a wake-up call, spurring efforts to track and deflect potential threats. Today, projects like the Asteroid Terrestrial Impact Last Alert System scan the skies nightly, while missions like DART have proven we can alter an asteroid's trajectory. The universe hasn't stopped hurling debris our way, but for the first time in history, we're learning how to fight back. The Tunguska Event is more than a historical curiosity. It's a cosmic warning shot, a reminder that the same forces that shaped our solar system's past still lurk in the present. The next time you hear about a close approach by an asteroid, remember, the difference between a near miss and a global catastrophe might come down to a few hours, a few miles, or the lessons we've learned from a mystery that still echoes through the Siberian taiga. Before Earth had its familiar moonlit nights, our planet endured a collision of unimaginable violence, a crash so monumental it shaped the very conditions for life itself. Picture a young solar system, still chaotic from its formation, when a rogue world roughly the size of Mars, dubbed Theia by scientists, slammed into early Earth. This wasn't a glancing blow. The impact was so colossal it vaporized rock, melted entire continents worth of material, and sent a glowing plume of debris arcing into space. For hours, our planet wore a crown of molten fire, its surface transformed into a seething ocean of magma. What happened next was even more extraordinary. That ejected debris didn't just scatter aimlessly. Gravity began pulling the fragments together, sculpting them into a new celestial body right before Earth's eyes. Within just a few centuries, a blink in cosmic time, the moon coalesced from that chaos, beginning its eternal dance around our planet. But this wasn't just any moon. Its birth left Earth with gifts that would echo through billions of years. The moon's gravitational pull became Earth's invisible anchor, stabilizing what had been a wobbly, erratic rotation. Without that steadying hand, our planet might have tumbled through space with wild axial tilts, triggering extreme climate swings that could have made complex life impossible. Then there are the tides, those rhythmic pulses of the oceans, driven by the moon's tug. Early Earth shorelines became laboratories where the constant ebb and flow of water may have helped concentrate the chemical building blocks of life, stirring primordial soups where the first organic molecules could form. Evidence of this cataclysm is written in the moon itself. Apollo astronauts brought back rocks that revealed a startling truth. The moon's composition is eerily similar to Earth's mantle. It's as if someone scooped out a piece of our planet's interior and flung it into orbit. Computer simulations of the impact show how Theia's core likely merged with Earth's, while lighter mantle material was ejected to form the moon. Even the moon's orbit, tilted just 5 degrees from Earth's equator, hints at the angle of that fateful collision. But here's the twist. This violent beginning might explain why Earth became a cradle for life while other rocky worlds did not. Mars, for instance, has 2 tiny, irregular moons, likely captured asteroids, that exert almost no stabilizing influence. Its axis wobbles wildly over time, contributing to drastic climate shifts that may have doomed any chance for complex ecosystems. Venus, meanwhile, spins backward with no moon at all, its surface a scorching hellscape. Theia's catastrophic gift didn't just give us a nightlight, it handed Earth the cosmic luck needed to nurture biology. The next time you gaze up at the moon, remember, you're looking at a piece of Earth itself, a relic of our planet's most formative trauma. That serene silver disk is the scar of a collision that could have shattered both worlds, but instead it forged a partnership billions of years in the making. The universe doesn't just build with gentle hands. Sometimes it takes a catastrophe to create the perfect conditions for wonder. In the summer of 1054, a new star blazed in the sky so brightly it was visible even during the day, a celestial beacon that stunned observers from China to the Middle East. This wasn't a star being born, it was one dying in spectacular fashion, a supernova so powerful its light crossed 6,500 years of space to reach Earth. Today, we know this event as the birth of the Crab Nebula, a swirling cloud of gas and dust that hides one of the universe's most fascinating objects at its heart, a pulsar spinning 30 times every second, the rapidly beating corpse of the star that once was. What makes this cataclysm so extraordinary isn't just its brilliance, it's the way it shaped our understanding of stellar death. When that massive star exhausted its nuclear fuel, its core collapsed in seconds, compressing matter so tightly that protons and electrons fused into neutrons, forming a city-sized sphere of unimaginable density. The outer layers, meanwhile, rebounded off this newborn neutron star in a shockwave that tore the star apart, hurling its guts across space at 5 million miles per hour. The result, a nebula that's still expanding today, its filaments glowing with the energy of particles whirling at nearly the speed of light. But the real marvel lies in what's left behind. That spinning neutron star, no larger than Manhattan but weighing more than our sun, is a cosmic lighthouse beaming out radiation with such precision that its pulses arrive like clockwork. Astronomers have used this regularity to test Einstein's theory of relativity, study the behavior of matter under extreme gravity, and even map the magnetic fields threading through interstellar space. The Crab pulsar doesn't just spin, it powers the entire nebula around it, energizing the gas so intensely that the cloud emits light across the electromagnetic spectrum, from radio waves to gamma rays. Here's what's truly wild. We're watching this cataclysm in slow motion. The light from the explosion reached Earth nearly a millennium ago, but the nebula's expansion is still unfolding before our telescopes. Time-lapse images taken decades apart show tendrils of gas creeping outward, their intricate shapes sculpted by the pulsar's fierce winds. And hidden in those glowing filaments are clues about how supernovas seed the universe with heavy elements, the same elements that make up planets, oceans, and life. The Crab Nebula is more than a relic. It's a living laboratory, offering front-row seats to the aftermath of a stellar catastrophe that's still reverberating through space. Every flicker of its pulsar, every shimmer of its twisted gases, tells a story about how death in the cosmos isn't an end, it's a transformation. And thanks to meticulous records kept by 11th century astronomers, we have a rare cosmic timeline, a chance to connect human history with the life cycle of the stars themselves. So the next time you gaze at the Crab Nebula through a telescope, remember, you're not just seeing a cloud of debris, you're witnessing the echo of a star's final act, a cataclysm that centuries after it faded from Earth's skies still teaches us how the universe recycles destruction into creation. In late 2019, one of the night sky's most recognizable stars began behaving strangely. Betelgeuse, the crimson-hued shoulder of the constellation Orion, dimmed so dramatically that even casual stargazers noticed its fading glow. By early 2020, the red supergiant had lost nearly 2/3 of its usual brightness, a change so extreme it sparked global speculation. Was this the prelude to one of the most spectacular cosmic events humanity could witness, a supernova visible in broad daylight? Theories swirled as astronomers scrambled to explain the Great Dimming. Some suggested Betelgeuse had simply coughed up a massive dust cloud, temporarily obscuring its light. Others wondered if the star's surface had cooled in patches, dimming its output. But the most tantalizing possibility was that this could be the first act of a stellar death throes, a sign that Betelgeuse, already in the final volatile stages of its life, was preparing to explode. Considering its size, if placed in our solar system, its outer layers would swallow Jupiter. Such an event would outshine the full moon, casting shadows at night and remaining visible for weeks. What makes Betelgeuse's behavior so fascinating isn't just its potential to explode. It's the rare chance to study a star in real time as it nears the end of its life cycle. Unlike the Crab Nebula's supernova witnessed centuries after the fact, Betelgeuse offers a front-row seat to the final chapters of a stellar giant's existence. Telescopes captured unprecedented details during its dimming episode, vast convective cells of plasma bubbling on its surface, and infrared observations revealing a titanic belch of dust, enough material to form a small moon ejected from the star's southern hemisphere. Here's the twist: Betelgeuse's explosion isn't just inevitable, it might have already happened. Located about 640 light-years away, the light we see today left the star in the 14th century. If it went supernova tomorrow, we wouldn't know until the 27th century. Yet even in its current state, the star serves as a cosmic laboratory. Its pulsations, regular cycles of brightening and dimming, provide clues about how massive stars redistribute material before their final collapse. And when it does explode, the event will shower nearby space with heavy elements, seeding future generations of stars and planets with the building blocks of life. For now, Betelgeuse has regained much of its brightness, but the questions linger. Every flicker, every subtle change in its light is a whisper from a star on borrowed time. Whether its final act comes next year or in 10,000 years, one thing's certain: when it happens, it'll rewrite the night sky and our understanding of stellar evolution in an instant. Until then, we watch, we study, and we wait, reminded that even the mightiest stars are fleeting actors in the universe's grand drama. Far beyond the orbits of Neptune and Pluto, in the frigid outskirts of our solar system, lies a vast and mysterious realm, the Oort cloud. This spherical shell of icy debris stretches nearly a light-year from the Sun, a graveyard of ancient comets left over from the solar system's birth. Most of these frozen wanderers drift in perpetual darkness, undisturbed for billions of years, until something nudges them from their slumber. That something could be as subtle as the Milky Way's own gravity. As our solar system orbits the galaxy's center, it bobs up and down through the galactic plane like a carousel horse, creating tidal forces that occasionally tug loose a comet from the Oort cloud's tenuous grip. Other times, the culprit is a passing star, an interstellar visitor drifting close enough to stir the cloud's frozen inhabitants with its gravity. When either of these disturbances occurs, the results can be dramatic. A dislodged comet begins a slow, elliptical journey inward, falling toward the Sun over thousands or even millions of years, its trajectory a cosmic roll of the dice. What makes these perturbations so fascinating is their unpredictability. Unlike the orderly orbits of planets, an Oort cloud comet's path depends entirely on the initial nudge it receives. Some swing harmlessly through the outer solar system before retreating back into the void. Others are flung entirely out of the solar system, becoming interstellar nomads. But a few, those that get just the right gravitational kick, aim straight for the inner solar system, transforming from silent ice balls into blazing comets with tails stretching millions of miles. History offers sobering examples of what happens when these icy intruders arrive. Comet Hale-Bopp, which lit up skies in 1997, likely originated in the Oort cloud, as did the Great Comet of 1843, whose tail stretched nearly 200 million miles. But not all encounters are so benign. Some researchers believe the Younger Dryas impact hypothesis, a controversial theory suggesting a comet or comet fragments struck Earth around 12,800 years ago could explain sudden climate shifts that affected early human civilizations. Whether or not that particular theory holds, the risk remains. Every comet dislodged from the Oort cloud is a potential wild card, capable of reshaping planetary climates if its path crosses ours. Yet there's a beautiful irony to this celestial chaos. The same icy bodies that could one day threaten Earth also carry secrets about our origins. Oort cloud comets are time capsules, preserving pristine material from the solar system's earliest days. When we study their composition, as missions like the European Space Agency's Rosetta did with Comet 67P, we're analyzing the same building blocks that once swirled in the protoplanetary disk, untouched by billions of years of solar heating. So while the Oort cloud's perturbations might seem like distant, abstract events, they're part of an ongoing dance that connects the farthest reaches of our solar system to the planets and life closer to home. Every comet that streaks through our skies is a reminder, even in the apparent stillness of space, nothing is truly at rest. The universe is always stirring the pot, sending ancient messengers our way, each one a story waiting to be deciphered. At the heart of our galaxy, hidden behind thick veils of dust and stars, lurks a sleeping giant, Sagittarius, a star, a supermassive black hole 4 million times heavier than our Sun. For most of its existence, this cosmic behemoth has been relatively quiet, a faint whisper in the radio spectrum, but astronomers have uncovered startling evidence that it wasn't always so peaceful. Roughly 3.5 million years ago, a blink in cosmic time, our galactic center erupted in a flare so powerful it sent cones of high-energy radiation screaming through the Milky Way at nearly the speed of light. This wasn't just a flicker, it was a full-blown tantrum, an outburst violent enough to scorch the atmospheres of planets tens of thousands of light years away. We know about this cataclysm because of ghostly imprints it left behind. In the Magellanic Stream, a ribbon of gas trailing our galaxy's two largest satellite galaxies, scientists detected strange patches of ionized particles, regions where atoms had been violently stripped of electrons. The only explanation, a sudden blast of extreme ultraviolet and X-ray radiation, emanating directly from the galactic center. The timing matches another clue, Fermi Bubbles, colossal structures of hot gas ballooning above and below the Milky Way's disk, stretching 50,000 light-years into space. These towering remnants are the afterglow of that ancient explosion, cosmic scars from when Sagittarius, a star, woke up hungry. What could trigger such a violent awakening? The leading theory involves an unfortunate star or gas cloud straying too close to the black hole's event horizon. As tidal forces ripped it apart, the doomed material spiraled inward, superheating to millions of degrees before vanishing, but not before unleashing a torrent of energy equivalent to 1 million supernova. The shockwaves from this feast would have rippled through nearby molecular clouds, compressing them and potentially triggering waves of new star formation. It's a paradox. The same forces that could sterilize planets might also create the conditions for new solar systems to emerge. This cycle of destruction and creation isn't unique to our galaxy. Observing other supermassive black holes, like the one powering the quasar 3C273, we've seen how these outbursts can sculpt entire galaxies. Jets of particles shot from their poles carve out cavities in intergalactic gas, while radiation pressures regulate star formation like a cosmic thermostat. Sagittarius, a star's flares were likely gentler by comparison, but their effects may still be written into the DNA of our galactic neighborhood, the most unsettling realization. This could happen again. Right now, a gas cloud called G2 is on a looping orbit that'll bring it dangerously close to our black hole within decades. While it's probably too small to trigger another major outburst, its fate will give astronomers a front-row seat to how black holes feed and what happens when they wake up. For now, we're safe, but the next time you look toward the constellation Sagittarius, remember, the giant at the center of our galaxy might be sleeping, but it's never truly silent. Its past roars echo through the cosmos, reminding us that even the quietest corners of the universe can hold the potential for unimaginable violence. On September 1st, 1859, the skies above Earth erupted in a spectacle unlike anything recorded in human history. Auroras, normally confined to polar regions, blazed so brightly over the Caribbean that birds began singing at midnight, mistaking the crimson and emerald glow for dawn. In Colorado, gold miners woke up and started making breakfast, convinced the sun had risen hours early. Newspapers reported that the light was bright enough to read by, even at midnight. But this celestial light show was no harmless anomaly. It was the signature of a solar superstorm so powerful it temporarily rewrote the rules of Earth's relationship with its star, an event we now call the Carrington Event, named after the British astronomer who witnessed its first violent flare through his telescope. What made this solar storm extraordinary wasn't just its beauty, it was its brute force impact on human technology, primitive as it was at the time. Telegraph systems, the 19th century's internet, went haywire worldwide. Operators in Europe and North America reported sparks leaping from their equipment, some severe enough to start fires. Even after disconnecting their batteries, many found their lines still carried enough induced current to send messages, as if the atmosphere itself had become a power source. In Philadelphia, a telegraph operator famously tapped out a message to his colleague in Pittsburgh. "I am not working my battery at all, are you?" The reply came back, "No, we are working on the auroral current." Modern analysis reveals why this happened. The Carrington Event was actually two punches from the sun. First, an intense solar flare, a magnetic explosion on the sun's surface, released a pulse of X-rays that reached Earth in just 8 minutes, ionizing our upper atmosphere. Then, a coronal mass ejection CME, a billion-ton cloud of magnetized plasma, barreled into our planet's magnetic field at over 4 million miles per hour. When that tsunami of charged particles collided with Earth's magnetosphere, it generated electric currents so strong they surged through telegraph wires, railroad tracks, and any other long conductors available. Here's what keeps space weather experts awake at night. If a Carrington-level storm struck today, the consequences would dwarf 19th century telegraph fires. Our power grid's vast networks of transformers and transmission lines would become unwitting antennas for these geomagnetic currents. Simulations suggest continent-scale blackouts could last months while engineers replace fried transformers, each one a custom-built behemoth requiring years to manufacture. Satellite communications would falter as charged particles fried delicate electronics in orbit. GPS signals would distort, potentially throwing off navigation by hundreds of feet. Even water and fuel supplies could be disrupted as electric pumps failed without power. The frightening reality is that we've narrowly missed repeats of the Carrington Event in recent decades. In 1989, a far weaker solar storm blacked out Quebec's power grid for 9 hours. In 2012, a CME of similar magnitude to the 1859 event missed Earth by just 9 days, a cosmic near miss that could have caused an estimated $2 trillion in global damages. Unlike hurricanes or earthquakes, solar storms give no tangible warning until their light reaches us 8 minutes before impact for flares, anywhere from 18 hours to several days for CMEs. Yet there's hope on the horizon. Space agencies now monitor the sun around the clock with fleets of satellites like NAS, a solar dynamics observatory, and the European Space Agency's solar orbiter. Early warning systems could give grid operators precious hours to shut down vulnerable infrastructure before a storm hits. Engineers are hardening transformers with protective circuits, while some nations like the UK have begun stockpiling spare equipment. Perhaps most crucially, scientists are learning to predict solar outbursts by mapping the sun's complex magnetic fields, where these storms originate. The Carrington Event wasn't just a historical curiosity, it was a wake-up call from the universe. Our sun, often pictured as a gentle life-giver, remains a dynamic star capable of violent outbursts. As our civilization grows more dependent on fragile electronics, we're simultaneously more vulnerable and better prepared than ever before. The difference between a modern Carrington becoming a manageable incident or a global catastrophe may come down to how seriously we heed the lessons written in those 1859 auroras, not just as beautiful anomalies, but as harbingers of a threat that's been hanging over us since the first telegraph operator saw his equipment spark to life under an electrified sky. The universe holds its greatest secrets in plain sight, or rather, in plain darkness. Imagine a spiderweb stretched across billions of light years, its strands glistening with galaxies. Now picture something far stranger. That entire cosmic structure is draped over an invisible scaffold, a hidden architecture of gravity woven from a substance we've never seen or touched. This is the realm of dark matter halos, the ghostly skeletons upon which galaxies are built. These halos aren't just passive backdrops, they're dynamic, living structures that dictate the rules of cosmic motion. Take our own Milky Way. Stars on its outer edges orbit at speeds that defy Newtonian physics, whirling so fast they should fling themselves into the void. The only explanation: an immense, unseen mass, a dark matter halo 10 times heavier than all visible stars and gas combined, anchoring them with its gravitational grip. Without these invisible giants, galaxies would fly apart like shattered pinwheels, their stars scattering into the abyss. But dark matter's influence stretches far beyond single galaxies. Peer into the cosmic web, the vast network of galaxy clusters and filaments spanning the universe, and you'll find dark matter's fingerprints everywhere. Computer simulations reveal how these halos formed first in the early universe, their gravity acting like cosmic glue, pulling ordinary matter into their embrace. Where halos clustered most densely, galaxies blossomed. Where they thinned out, voids stretched for hundreds of millions of light years. The universe's large-scale structure isn't random. It's a shadow play orchestrated by dark matter. Here's the twist: we've never directly detected a single particle of this mysterious substance. Everything we know comes from watching its gravitational effects, like tracking a burglar by footprints in the snow. Some theories suggest dark matter could be WIMP, weakly interacting massive particles that barely interact with normal matter. Others propose actions, hypothetical particles so light they behave more like waves. Then there's the radical idea that dark matter doesn't exist at all, that our understanding of gravity itself needs rewriting. Yet the evidence for dark matter halos keeps mounting. When galaxies collide, like in the famous Bullet Cluster, their visible gas slams together and heats up while their dark matter cruises right through, revealed only by how its gravity bends distant starlight. Even more telling, tiny satellite galaxies orbiting the Milky Way align in a flat plane, a configuration that only makes sense if they're tracing the contours of an immense, invisible sphere. The most mind-bending realization: dark matter halos might not just shape galaxies, they could determine their fate. Simulations show these halos growing hierarchically, merging and cannibalizing smaller ones over billions of years. Our own Milky Way's halo likely contains the remnants of dozens of devoured dwarf galaxies, their stars now swirling in a ghostly graveyard. And when Andromeda collides with us in 4 billion years, their dark matter halos will merge first, dictating how the visible wreckage unfolds. So while dark matter refuses to reveal itself directly, its influence is written across the cosmos in the spin of galaxies, the architecture of the cosmic web, and even the trajectory of light itself. The next time you gaze at the night sky, remember, what you see is just the glittering surface. The real cosmic drama plays out in the dark. Among the most breathtaking sights in the cosmos, the pillars of creation stand like ancient sentinels in the Eagle Nebula, towering columns of gas and dust where new stars are born. But these iconic structures are living on borrowed time. Right now, shockwaves from nearby supernova are carving away at them, molecule by molecule, in a slow-motion demolition that's as beautiful as it is destructive. What makes this cataclysm so fascinating isn't just the inevitable collapse of these cosmic spires, it's the paradox they embody. Even as they crumble, they're setting the stage for the next generation of stars to rise from their ashes. The process works like an interstellar domino effect. When a massive star explodes as a supernova, it sends out a supersonic shockwave that ripples through surrounding gas clouds. As these waves slam into the pillars of creation, they compress the gas, triggering pockets of it to collapse under gravity's pull. Some of these collapsing knots will grow dense and hot enough to ignite nuclear fusion, becoming newborn stars. In other words, the same forces tearing the pillars apart are also jump-starting the birth of their successors. It's a celestial cycle of destruction and creation playing out over millions of years. Hubble's famous images capture the pillars in stunning detail, but what they don't show is the invisible clock ticking down. By analyzing the structure's shapes and the movement of nearby stellar winds, astronomers estimate the pillars have maybe another 100,000 years left, a blink in cosmic terms. Some sections are already vanishing faster than others, sculpted into eerie, finger-like projections by the relentless erosion. Yet hidden within those crumbling towers are protostars' faint, embryonic suns still wrapped in cocoons of gas. When the pillars finally disintegrate, these fledgling stars will be set free, their light no longer obscured by the dense clouds that birthed them. There's a poetic irony here. The very supernova dooming the pillars of creation were likely born in similar stellar nurseries eons ago. Their explosions now echo through the nebula, returning heavy elements forged in their cores back to the cosmic forge. Oxygen, carbon, iron, the building blocks of planets and life, are being scattered into space, ready to be incorporated into future worlds. So while the pillar's demise might feel like a loss, it's really just the universe's way of recycling stardust into new possibilities. What's happening in the Eagle Nebula isn't unique, it's the rule, not the exception. Across the galaxy, shockwaves from supernova and stellar winds are constantly reshaping nebulae, tearing down old structures to make way for new ones. The difference is that we've caught this one in the act, giving us a front-row seat to a process that's usually too slow for human eyes to witness, and that's the real gift of the pillars of creation. They're not just a snapshot of stellar birth, they're a living lesson in how the cosmos thrives on change, proving that even the most breathtaking wonders are fleeting brushstrokes in an ever-evolving masterpiece. In 1977, as disco music filled the airwaves and home computers were still a futuristic dream, NASA launched two robotic pioneers on a one-way journey into the unknown. The Voyager probes, each no larger than a compact car, embarked on what would become humanity's most audacious road trip, venturing farther from home than any human-made object in history. But their true milestone came decades later, when these time capsules of 20th century engineering did something extraordinary. They slipped free of the sun's embrace, crossing the invisible boundary where our star's influence wanes and the true interstellar void begins. This boundary, called the heliopause, isn't a hard wall, it's a turbulent frontier where the solar wind, that stream of charged particles rushing outward from the Sun, finally collides with the interstellar medium, the thin soup of gas and dust filling the space between stars. For years, scientists debated where exactly this border lay. Then, in August 2012, Voyager 1's instruments told a startling story. The solar wind particles around it plummeted to near zero, while cosmic rays from distant galaxies surged tenfold. The probe had entered uncharted territory, becoming the first human artifact to taste the raw stuff of the galaxy itself. What makes this crossing so profound isn't just the distance, over 11 billion miles from Earth at the time, but what it represents. For the first time, humanity placed a footprint beyond the cradle of our solar system. Voyager's exit marked the moment we transitioned from a species bound to its home star to one capable of reaching into the galactic neighborhood. And the data it sent back shattered expectations. The interstellar medium wasn't the calm, uniform sea many predicted. Instead, Voyager found a region of frothy magnetic bubbles where charged particles from the Sun and cosmic rays from deep space engaged in a chaotic dance. Yet the Voyager's journey is far from over. Even as you watch this, they're still transmitting their signals, now weaker than a refrigerator light bulb, taking over 20 hours to reach Earth. Each ping carries priceless data about the conditions at the solar system's edge, helping scientists map the invisible magnetic highways that guide cosmic rays and the subtle pressure of starlight pushing against the heliosphere. These golden records aboard them, etched with sounds, images, and greetings from Earth, may one day be the only trace of our civilization left in the universe. There's something deeply humbling about these twin emissaries drifting through the dark. They carry no engines to steer them, no brakes to slow them. They're cosmic driftwood now, subject to the whims of galactic currents. In 40,000 years, Voyager 1 will float within 1.6 light-years of a star in Camelopardalis. Voyager 2, on a different trajectory, will pass near Sirius in 296,000 years. Their journeys will outlast not just our lifetimes, but likely our species, our planet, even our Sun's eventual expansion into a red giant. The Voyager's silent odyssey forces us to confront our place in the cosmos. They're proof that even in a universe shaped by cataclysms, supernova, galactic collisions, and stellar nurseries, the quietest acts of exploration can ripple across time. These probes weren't propelled by explosions or cosmic violence, but by human curiosity. And though they'll never reach another star, they've already achieved something revolutionary. They've made the vast, impersonal galaxy feel just a little bit smaller, a little more knowable. So the next time you hear about a distant exoplanet or a far-off galaxy, remember we've already taken our first tentative step into that great beyond. Not with warp drives or generation ships, but with two resilient machines, their golden record spinning silently in the dark, carrying whispers of Earth into the endless night. Their quiet crossing of the heliopause wasn't just a scientific milestone. It was the universe's way of reminding us that even the longest journeys begin with a single, fragile step. On August 17, 2017, the universe sent Earth a message written in ripples of space-time and bursts of gamma rays, a cosmic telegram announcing the violent merger of two neutron stars 130 million light-years away. This event, catalogued as GW 170817, wasn't just another astrophysical curiosity. It was the first kilonova ever observed with both gravitational waves and light, a breakthrough that cracked open one of astronomy's longest-standing mysteries, where the heaviest elements in the universe are forged. Neutron stars are the densest objects in existence outside black holes, city-sized remnants of supernova, so compact that a single teaspoon of their material would weigh 1 billion tons. When two of these stellar corpses spiral into each other, the collision unleashes energies beyond comprehension. As they merged, GW170817 ejected material at nearly the speed of light, creating a fireball 1,000,000 times brighter than our Sun. But the real magic happened in the debris. The extreme conditions, temperatures exceeding 1,000,000,000,000 degrees and pressures strong enough to crush atoms, transformed ordinary matter into gold, platinum, uranium, and other heavy elements in a process called rapid neutron capture, or the R process. Before this detection, scientists had theorized that kilonovae might be cosmic alchemists, but GW170817 delivered proof. Spectroscopic analysis of the afterglow revealed unmistakable signatures of precious metals being synthesized in real time. The numbers are staggering. This single event likely produced hundreds of Earth masses worth of gold and platinum, scattering them across interstellar space like cosmic glitter. Suddenly, the origins of the gold in your wedding ring or the platinum in a catalytic converter traced back to collisions like this one, happening billions of years ago in distant galaxies. The discovery also solved another puzzle. For decades, astronomers had noticed that heavy elements seemed curiously absent from the early universe. Now we know why. It took time for the first generation of massive stars to live, die, and leave behind neutron stars, which then had to pair up and merge. The cosmic gold rush couldn't begin until these dense stellar remnants started colliding, seeding galaxies with the ingredients for rocky planets, and eventually life. What makes GW170817 truly revolutionary is how it was detected. Gravitational wave observatories like LIGO and Virgo felt the space-time ripples from the neutron star's death spiral, while telescopes across the electromagnetic spectrum, from gamma rays to radio waves, captured the aftermath. This multi-messenger astronomy gave us a 3D movie of a cosmic cataclysm, with each wavelength revealing a different chapter of the story. Gamma rays confirmed the relativistic jets, optical light showed the radioactive glow of freshly minted elements, and infrared observations caught the telltale heat of lanthanide's rare earth metals forged in the chaos. But perhaps the most humbling realization is how fleeting these events are. The entire merger from the final orbits to the explosive aftermath unfolded in less than 2 minutes. In that brief window, the universe conducted a symphony of physics, general relativity, nuclear physics, and plasma dynamics all intertwining to create something new. And thanks to an unprecedented global collaboration of observatories, humanity had front-row seats. GW170817 didn't just change our understanding of heavy elements. It revealed how interconnected the cosmos truly is. The same forces that shaped galaxies and birthed stars also crafted the atoms in our bodies and the technology in our hands. Every time you hold a piece of jewelry or look at a satellite image, you're touching the legacy of neutron star collisions. A reminder that even the most violent events in the universe can leave behind something precious. Somewhere beyond the stars we see, beyond even the farthest edges of our cosmic maps, lurks a mystery so massive it's tugging entire galaxies toward it against the expansion of the universe itself. Astronomers call it the Great Attractor, a gravitational behemoth hidden behind the dense stars and dust of our own Milky Way's disk. For decades, this invisible force has been pulling our local group of galaxies, including Andromeda, the Milky Way, and dozens of smaller neighbors toward it at a staggering 14 million miles per hour. That's enough speed to cross the entire United States in less than a second. Yet despite its overwhelming influence, we've never directly seen what's causing it. The discovery began with an anomaly in the cosmic microwave background, the afterglow of the Big Bang. Scientists noticed our galaxy wasn't just drifting with the universe's expansion. It was racing toward a specific patch of sky near the constellations Centaurus and Hydra. Early measurements in the 1970s revealed hundreds of nearby galaxies sharing this strange motion, all drawn toward what appeared to be a gravitational focal point roughly 250 million light-years away. The problem, when they pointed telescopes in that direction, they found nothing, or rather, nothing obvious. Our view was blocked by the Milky Way's own galactic bulge, a thick band of stars and dust so dense it obscures nearly 20% of the visible universe beyond. X-ray observations eventually pierced this cosmic veil, revealing an unsettling truth. The Great Attractor isn't a single supermassive object, but an immense confluence of galaxy clusters, the Norma cluster at its heart, surrounded by thousands of galaxies bound together in a gravitational dance. Combined, they weigh as much as 100 quadrillion suns, yet even this colossal structure couldn't fully explain the observed pull. The real shock came when astronomers mapped motions on an even grander scale and found something bigger, the Laniakea supercluster, a web of 100,000 galaxies spanning 500 million light-years, with the Great Attractor as its gravitational center of mass. Here's where it gets eerie. Laniakea itself appears to be in motion, pulled toward an even more massive structure called the Shapley supercluster, a gathering of galaxy clusters so vast it defies comprehension. It's as if the universe is built like a set of nesting dolls, each layer revealing a larger, more dominant gravitational force. The Great Attractor, then, is just one link in a chain of cosmic puppeteers, each tugging the other in an endless hierarchy of influence. What does this mean for our corner of the cosmos? Over billions of years, the relentless pull of the Great Attractor will reshape our local galactic neighborhood. The Milky Way, Andromeda, and their satellite galaxies will continue their march toward this invisible master, eventually merging with the Norma cluster in a collision that will make the future Milky Way-Andromeda merger look like a fender bender. But here's the twist. By the time we get there, the universe's accelerating expansion may have stretched space so much that the Great Attractor's grip will weaken, leaving our descendants forever approaching, never arriving. The most humbling lesson of the Great Attractor isn't just about hidden mass or cosmic motion. It's a reminder of how little we truly see. For all our telescopes and technology, the universe still holds cards close to its chest. What else lies beyond our view, bending the paths of galaxies and rewriting the fate of everything we know? The answer might be out there, waiting in the dark, not just pulling us toward it, but pulling back the curtain on how little we understand about the cosmic stage we call home. Rising like colossal hourglasses from the heart of our galaxy, the Fermi Bubbles stretch 25,000 light-years above and below the Milky Way's disk, towering monuments to a cataclysm we barely witnessed. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these twin lobes of ultra-high-energy radiation glow faintly in gamma rays, invisible to human eyes but revealing a violent secret. Our galaxy's supermassive black hole threw a tantrum of cosmic proportions sometime in the past few million years. What makes these structures so astonishing isn't just their scale. You could fit 100 Milky Ways stacked vertically within their height, but their composition. The bubbles are filled with particles moving near light speed, their gamma-ray emission betraying the presence of cosmic rays slamming into interstellar gas. Their edges are razor-sharp, suggesting whatever event created them was sudden and explosive, like a champagne cork popping from a bottle. Yet the energy required to inflate such structures is mind-boggling, equivalent to 100,000 supernovae detonating simultaneously at the galaxy's core. The leading suspect, Sagittarius, a star, our galaxy's central black hole, gorging itself on an unusually large meal. One theory suggests a doomed gas cloud wandered too close, its material stretched into a swirling disk as it spiraled toward oblivion. Friction within this disk would have heated it to millions of degrees, generating powerful magnetic fields that funneled some of the infalling matter into jets erupting perpendicular to the galactic plane. These jets, pumping out energy for thousands or even millions of years, would have blown the Fermi bubbles like cosmic soap bubbles, inflating them with hot plasma and relativistic particles. But there's a twist in this tale. The bubble's symmetrical shape and crisp boundaries challenge our understanding of black hole outbursts. Simulations show such structures should be messy, warped by the galaxy's rotation and interstellar winds. The Fermi bubble's pristine form hints at something more refined, perhaps periodic burps from Sagittarius, a star, with each outburst carving out a cleaner cavity in the galactic halo. Supporting this idea are the so-called E-Rosetta bubbles, detected in 2020 in X-rays, which appear to be older, fainter cousins to the Fermi structures, suggesting our black hole has a history of such eruptions. Hidden within these glowing bubbles lies a cosmic irony, destruction begetting creation. As the high-energy particles collide with cooler gas at the bubble's edges, they generate shock waves that compress interstellar material, potentially triggering star formation. Some astronomers speculate that our galaxy's central region experienced waves of stellar birth following these outbursts, with newborn stars inheriting heavy elements forged in the black hole's violent vicinity. Even the bubbles themselves serve a purpose, acting as pressure release valves for the galaxy, preventing the central black hole from overheating its surroundings and stifling star formation entirely. The most humbling realization: we're likely witnessing just the latest chapter in an ongoing saga. Other galaxies show evidence of similar, sometimes far more dramatic outbursts. The nearby M87 galaxy, for instance, sports jets stretching thousands of light years, visible even in amateur telescopes. The Fermi bubbles may be our galaxy's relatively modest contribution to this universal phenomenon, a reminder that even quiet black holes like Sagittarius, a star, have moments of spectacular violence. Right now, as you read this, those faint gamma-ray ghosts continue to expand, their particles slowly diffusing into intergalactic space. They carry with them a message from the galaxy's core, that even the darkest hearts of galaxies can shape their surroundings in ways we're only beginning to understand. The Fermi bubbles aren't just relics of a past explosion, they're living proof that our galaxy breathes, erupts, and evolves, writing its history in light we're only now learning to read. For billions of years after the Big Bang, the universe was a silent, lightless expanse, a sea of hydrogen and helium so dark you could stare across it for eternity and see nothing. No stars, no galaxies, just an endless cosmic night stretching in every direction. Then, somewhere around 100 to 200 million years after creation, something extraordinary happened. A faint spark flickered in the void, then another and another. Like fireflies waking in a vast meadow, the first stars began to glow, piercing the darkness and igniting what astronomers call the cosmic dawn, the moment light conquered the universe's eternal night. These pioneer stars weren't like the ones we know today. Born from pristine clouds of hydrogen and helium uncontaminated by heavier elements, they grew to staggering sizes, some hundreds of times more massive than our sun, burning at temperatures that would make modern stars look like candle flames. Their brilliance came at a cost. These stellar titans lived fast and died young, exhausting their nuclear fuel in just a few million years before collapsing in spectacular supernova. But in their brief, fiery lives, they accomplished something revolutionary. They transformed the universe from a simple place of basic atoms into a complex chemical factory, forging the first heavy elements like carbon, oxygen, and iron in their cores, the raw materials for everything that followed. The cosmic dawn didn't just light up the cosmos, it fundamentally changed its structure. Ultraviolet radiation from those first stars began breaking apart nearby hydrogen atoms, a process called reionization that slowly made the universe transparent to light. Imagine fog lifting across an entire continent, except this fog had blanketed all of existence. Over hundreds of millions of years, bubbles of ionized gas expanded and merged until the entire cosmos became visible for the first time, setting the stage for galaxies to form and evolve. We know about this era not from direct observation. Those first stars are too distant and faint for even our best telescopes, but from their fingerprints on the cosmic microwave background. Satellite missions like Planck have detected subtle distortions in this ancient light, evidence of how those early photons interacted with the universe's growing transparency. Even more astonishing, radio astronomers are now tuning into frequencies that could reveal the cosmic dawn's actual sound. The faint radio whispers of hydrogen atoms absorbing ultraviolet light from those first stars, a signal that's been traveling through space for over 13 billion years. What's truly mind-bending is how delicate this transition was. Had the first stars formed slightly differently, burning too hot or too cold, dying too quickly or too slowly, the universe might never have developed the right conditions for galaxies like ours to form. The cosmic dawn wasn't just a switch flipping from dark to light. It was the universe's first fragile experiment with complexity, a trial run that set the rules for everything that came after. And in a very real sense, we owe our existence to those brief, brilliant giants whose light ended the long cosmic winter and made the universe we know today possible. The next time you look up at the night sky, remember, every star you see is descended from those first, daring pioneers. Their light may be gone, but their legacy shines on in every galaxy, every planet, every atom in your body that was forged in their fiery hearts. The cosmic dawn wasn't just the start of light, it was the moment the universe began building something greater than itself, and we're the living proof of how far that light can travel. Some of the universe's greatest mysteries aren't written in exploding stars or colliding galaxies, they're hidden in decimal places. Take the Hubble constant, a number so fundamental it dictates how fast the universe is expanding. For decades, astronomers calculated this cosmic speed limit with growing precision, confident their measurements would eventually converge. Then came the plot twist. Two of science's most trusted methods started giving wildly different answers, creating a rift in cosmology so deep we now call it the Hubble Tension. The first method acts like a cosmic ruler, using the flickering light of distant stars called Cepheid variables to measure intergalactic distances. The second approach reads the faint afterglow of the Big Bang itself, the cosmic microwave background, to extrapolate the universe's expansion history. Both techniques are meticulous, both have been refined over generations, yet they stubbornly disagree by about 9%. That might sound small, but in a field where measurements often agree to within decimal points, it's like two GPS devices giving directions to the same address, one sending you to New York, the other to Los Angeles. What makes this discrepancy so unsettling isn't just the math, it's what it implies about the fabric of reality. If both measurements are correct and repeated experiments suggest they are, our standard model of cosmology might be missing a crucial ingredient. Perhaps dark energy, the mysterious force accelerating the universe's expansion, isn't constant but changes over time. Maybe there's an unknown particle type subtly influencing cosmic growth, like an invisible hand tweaking the universe's tempo. Some theorists even speculate we're seeing echoes of a pre-Big Bang phase, a cosmic before that left fingerprints on how space stretches. The Hubble tension isn't just academic quibbling, it's a potential gateway to revolutionary physics. When similar cracks appeared in Newtonian mechanics centuries ago, they led Einstein to relativity. Today's discrepancies might be pointing toward an equally profound breakthrough, one that could rewrite our understanding of time, gravity, and the universe's ultimate fate. The most exciting possibility, that we're on the verge of discovering something entirely new about how existence works, hidden all along in the subtle mismatch between two sets of numbers. Right now, telescopes around the world and in space are racing to resolve the tension. The James Webb Space Telescope peers deeper into Cepheid variables than ever before, while next-generation cosmic microwave experiments like the Simons Observatory scour the sky for anomalies. Whatever they find, whether it's an overlooked measurement error or evidence of exotic physics, the outcome will reshape cosmology. Because sometimes the most earth-shaking discoveries don't come from booming explosions or dazzling light shows, but from the quiet, persistent whisper of data that refuses to add up. The Hubble Tension reminds us that the universe still holds cards close to its chest. After all our centuries of stargazing and decades of space exploration, fundamental questions about cosmic expansion remain unanswered. And that's the beautiful paradox of science. The moment we think we've got the universe figured out, it throws us a curveball, inviting us to look deeper, think harder, and marvel at how much we have yet to learn. Scattered across our galaxy, hidden in plain sight, are the celestial refugees of a cosmic feast, the last survivors of a dwarf galaxy torn apart by the Milky Way's gravity. Astronomers call this ancient wreckage the Gaia Sausage, not for its shape, but for the way its stars move, streaking through space like scattered crumbs from a long-finished meal. These stars don't orbit the galactic center in orderly spirals like our Sun. Instead, they plunge radially, diving in and out of the Milky Way's heart like comets on steroids, a telltale sign they weren't born here, but swallowed whole in a cataclysm that reshaped our galaxy forever. The discovery began with data from the Gaia spacecraft, a European mission mapping the positions and motions of over 1 billion stars with unprecedented precision. When researchers analyzed these stellar trajectories, they noticed something bizarre. Thousands of stars moving in these extreme, plunging orbits, all sharing similar chemical fingerprints, higher ratios of heavy elements like iron compared to the Milky Way's native stars. This wasn't random chaos. It was the ghostly signature of a dwarf galaxy roughly 10 billion years ago, perhaps 1/5 the Milky Way's current size, that strayed too close to our galaxy's gravitational pull. The collision wasn't a quick, violent crash. It was a slow, gravitational dismantling, a cosmic digestion that stretched over hundreds of millions of years. As the dwarf galaxy circled the Milky Way, tidal forces ripped it apart, stretching its stars into elongated streams that eventually dispersed, leaving behind this sausage-shaped pattern in their motions. But the real shock, the aftermath, didn't just leave debris. It triggered a wave of star formation as the dwarf galaxy's gas compressed Milky Way material, igniting new stellar nurseries. Some of those newborn stars might still shine today, mixed with the survivors of the original dwarf. Here's where it gets even wilder. The Gaia Sausage impact might explain one of the Milky Way's most puzzling features, its thickened disk. Before this merger, our galaxy was likely a flat, delicate spiral. The dwarf's gravitational punches stirred things up, puffing the disk into the layered structure we see now. It's as if the Milky Way swallowed a cosmic protein shake, bulking up in the process, and the feast didn't end there. The sausage remnants include some of the galaxy's oldest globular clusters, dense balls of stars like Messier 54, which may have once been the dwarf's crown jewel before being captured as a galactic trophy. What's truly humbling is how recent this discovery is. For centuries, these stars were right above us, hiding in datasets, Only with 21st century precision could we spot their shared motion, like picking out a whispered conversation in a crowded room. And they're not alone. The Milky Way's halo is littered with similar stellar streams, the remains of other, smaller galaxies consumed over time. The Gaia Sausage is just the most massive, the most dramatic example of our galaxy's cannibalistic past. So the next time you gaze at the night sky, remember, some of those twinkling lights aren't just stars. They're survivors of a lost kingdom, refugees from a shattered world, now forever part of our own. The universe doesn't just build galaxies, it merges them, tears them apart, and stitches their pieces into something new. And in the motions of those rogue stars, we're reading the diary of a cataclysm that helped make the Milky Way what it is today, a cosmic melting pot, still bearing the scars of its most violent meals. In the vast silence between galaxies, where darkness stretches for millions of light years, cosmic fireworks occasionally flare, brief, brilliant bursts of radio waves so powerful they outshine entire stars. Lasting just milliseconds, these fast radio bursts, or FRB, are among the most puzzling phenomena in modern astronomy. Imagine detecting a signal from halfway across the observable universe that carries more energy than the Sun emits in 80 years, all compressed into a blink so fast it could be missed between heartbeats. The first FRB was discovered in 2007, buried in archival data from Australia's Parkes Observatory. At first, astronomers debated whether it was even real, perhaps just a glitch from Earth-bound technology. But then more bursts appeared, each with a unique fingerprint, a telltale dispersion where higher frequencies arrived slightly earlier than lower ones, a signature of radio waves traveling through intergalactic plasma. This wasn't noise, this was a message from the cosmos, written in some of the most extreme physics nature has to offer. What generates these cosmic lightning strikes? Theories range from the dramatic to the downright bizarre. Magneta's neutron stars with magnetic fields 1 trillion times stronger than Earth's top the suspect list. Observations in 2020 confirmed at least one FRB originated from a magneta in our own galaxy, though its burst was thousands of times weaker than those from distant sources. Other possibilities include colliding neutron stars, evaporating black holes, or even, though highly speculative, signatures of advanced alien technology. The truth is, no single explanation yet fits all the data. Some FRBs repeat sporadically, while others are one-off events, suggesting multiple cosmic engines might be at work. The real magic of FRBs lies not just in their mystery, but in what they reveal about the universe's hidden structures. As these bursts travel across space, they pass through clouds of ionized gas and dark matter, subtly altering their radio waves like sunlight filtering through stained glass. By decoding these changes, astronomers have mapped the universe's missing matter, ordinary atoms that should exist but had evaded detection. It turns out, this elusive material is woven between galaxies in diffuse filaments, a cosmic web that FRBs help illuminate better than any telescope. Here's where the story takes an even wilder turn. In 2020, scientists detected an FRB from a galaxy so far away its light had traveled 8 billion years to reach us, making it the most distant fast radio burst ever recorded. The signal, labeled FRB 2022610A, was so energetic that in less than a millisecond, it released as much energy as our Sun emits over 30 years. Yet despite its power, the burst's host galaxy was surprisingly unremarkable, a modest, unassuming corner of the universe, proving these events can happen anywhere under conditions we're still struggling to understand. The hunt for FRBs is now a global race, with facilities like Canada's CHIME telescope detecting dozens of bursts monthly. Each new detection adds a piece to the puzzle, yet the full picture remains tantalizingly out of reach. One leading theory suggests repeating FRBs might come from neutron stars orbiting supermassive black holes, their magnetic fields twisted and snapped like rubber bands, releasing pent-up energy in sporadic bursts. Others propose cosmic comb models, where shockwaves from stellar collisions focus radio waves into narrow, intense beams. Perhaps the most humbling lesson of FRBs is how much we still don't know about the universe's most energetic phenomena. They remind us that for all our telescopes and supercomputers, the cosmos still holds surprises that defy expectations. Every time one of these bursts flickers onto our detectors, it's as if the universe is sending us a riddle, a challenge written in radio waves, urging us to look deeper, think bigger, and stay curious. And so the mystery endures. Are these bursts the death cries of exotic stars, the byproducts of cosmic collisions, or something even stranger, waiting beyond the edge of our current theories? One thing's certain, with each new FRB detected, we're not just collecting data. We're eavesdropping on the universe's most secretive conversations, 1 millisecond at a time. Our solar system isn't just drifting aimlessly through space, it's on a grand cosmic carousel ride, completing a full orbit around the Milky Way center every 230 million years. That means since the dinosaurs roamed, we've only traveled about 1/3 of the way around our galactic circuit. But this journey isn't a smooth cruise along a flat highway. The Milky Way's spiral arms, dense star clusters, and turbulent interstellar clouds create a dynamic obstacle course, exposing Earth to vastly different cosmic conditions as we weave through the galaxy's shifting neighborhoods. Right now, we're cruising through what astronomers call the local bubble, a relatively empty region of space carved out by ancient supernova, where the interstellar medium is thinner and cooler. This celestial safe zone stretches about 300 light-years across and shields us from the harsher radiation and debris found in denser parts of the galaxy. But this wasn't always the case. Roughly 10 million years ago, our solar system plunged through a molecular cloud so thick it could have compressed the heliosphere, Earth's protective magnetic bubble, to a fraction of its current size. Back then, cosmic rays' high-energy particles from exploded stars would have bombarded our planet at rates much higher than today, potentially influencing cloud formation and even evolution. The rhythm of our galactic orbit also syncs with Earth's long-term climate patterns in surprising ways. As we oscillate up and down through the Milky Way's disk, a motion that takes about 60 million years, we periodically cross the galaxy's crowded midplane, where interstellar gas and dust concentrate. Some researchers suggest these crossings correlate with increased comet activity, as gravitational perturbations send icy bodies from the Oort cloud hurtling inward. There's even tantalizing evidence linking these phases to mass extinction events, like the one that wiped out the dinosaurs. Whether it's through comet showers, heightened radiation, or other cosmic triggers, our position in the galaxy might subtly shape the story of life itself. But the most dramatic shifts come when we pass through one of the Milky Way's spiral arms. These star-forming regions, dense with young, hot stars and supernova remnants, are like cosmic storm zones. The last time we crossed one 300 million years ago, Earth was in the Carboniferous period, its lush forests laying the groundwork for today's coal deposits. The next spiral arm encounter, due in about 100 million years, could bathe the solar system in intense ultraviolet light and cosmic rays, forcing any future life to adapt or perish. Here's the twist: our galactic orbit isn't perfectly circular. It's slightly elliptical, meaning our distance from the Milky Way's supermassive black hole, Sagittarius A star, varies by thousands of light years over time. When we're closer, the gravitational tides are stronger, potentially stirring up more comets and asteroids in the outer solar system. Some simulations even suggest these tidal forces could nudge the hypothetical planet 9, if it exists, into a destabilizing orbit that sends icy worlds careening inward. Yet for all these potential hazards, our galactic journey has also brought gifts. Passing through supernova-enriched regions may have seeded our solar system with rare isotopes like iron-60, traces of which have been found in deep-sea sediments and lunar samples. These radioactive fingerprints tell us that about 2 million years ago, a dying star's debris rained down on our corner of space, depositing elements that could only form in a stellar explosion. The grand lesson here is one of cosmic interconnectedness. Earth doesn't exist in isolation, it's a passenger on a much larger voyage, one that ties our planet's fate to the galaxy's structure and history. From climate shifts to extinction events, from the composition of our oceans to the very atoms in our bodies, the Milky Way's gravitational dance leaves its mark in ways we're only beginning to decode. So the next time you gaze at the night sky, remember, you're not just looking at the stars, you're seeing the ever-changing neighborhood we pass through on our slow, stately march around the galaxy, a journey where every rotation writes new chapters in the story of our solar system. Right now, as you read these words, our solar system is floating inside a vast cosmic bubble, a region of space so empty it's like a cleared-out room in the otherwise crowded house of the Milky Way. This is the local bubble, a peanut-shaped cavity stretching roughly 300 light-years across, with Earth positioned slightly off-center. But don't let the name fool you, this isn't some peaceful void. It's the scar tissue left behind by a series of violent stellar explosions that reshaped our galactic neighborhood millions of years ago. The story begins about 14 million years in the past, when a cluster of massive stars, each one many times heavier than our Sun, reached the ends of their lives in quick succession. One after another, these giants exploded as supernova, their shockwaves carving out a growing cavity in the interstellar medium. Picture a group of underwater dynamite blasts, each one pushing water outward until they create a temporary hollow, except here, the water is thin gas and dust, and the hollow is big enough to swallow thousands of solar systems. These explosions didn't just clear out space, they also heated the remaining gas to millions of degrees, creating a diffuse, super-hot plasma that still lingers like a ghostly afterglow. What's astonishing is how this ancient violence might have touched life on Earth. Around the same time the local bubble was forming, our planet was undergoing dramatic climate shifts. The Miocene epoch saw global temperatures yo-yoing, with ice sheets expanding and retreating in cycles that scientists are still untangling. Some researchers speculate that as the solar system moved through regions of varying interstellar density, first compressed by molecular clouds, then entering the newly blown bubble, changes in cosmic ray exposure could have influenced cloud formation and atmospheric chemistry. It's a controversial idea, but not implausible. Higher cosmic ray flux has been shown to seed more low-altitude clouds, which reflect sunlight and cool the planet. The local bubble, then, might be more than a cosmic curiosity. It could be a silent player in Earth's climate history. Evidence for this supernova-sculpted bubble comes from multiple lines of observation. The stars nearest to us, including well-known ones like Alpha Centauri and Sirius, are all moving outward from a central point like shrapnel from a detonation. Radioactive isotopes like iron-60, found in deep-sea sediments and lunar regolith, match the expected debris from nearby supernova in both composition and age. Even the empty space inside the bubble isn't truly void. It's filled with an extremely thin, million-degree gas detected by its faint X-ray glow, the fading breath of those long-dead stars. The local bubble isn't a static structure, it's still evolving. Our solar system happens to be passing through one of its walls right now, a region where the bubble's hot interior meets cooler, denser interstellar clouds. In about 50,000 years, we'll exit the bubble entirely, entering environments with different radiation levels and cosmic particle densities. Who knows what effects that transition might bring? Here's the beautiful paradox of the local bubble. It's both a protective cocoon and a reminder of our vulnerability. Those supernova cleared out potentially dangerous interstellar debris, but they also demonstrate how stellar deaths light years away can ripple across epochs to touch our tiny world. We're not just inhabitants of a solar system or a planet. We're travelers in a dynamic, ever-changing galactic landscape, one where events older than human civilization still shape the space around us. And that's the ultimate lesson of the local bubble. In space, even the emptiness tells a story. Deep in the cosmic shadows, where light bends and vanishes, lurk some of the universe's most elusive predators, rogue black holes untethered from galaxies and drifting silently through the void. Unlike their supermassive cousins anchored at galactic centers, these wanderers are stellar mass black holes, the remnants of collapsed stars cast adrift by gravitational kicks during violent cosmic events. Picture a bullet fired through the darkness, invisible, unpredictable, and carrying enough gravitational might to warp entire star systems if they stray too close. Detecting these cosmic nomads is like searching for a shadow in a pitch-black room. Without accretion disks, the glowing rings of superheated material that typically betray a black hole's presence, they reveal themselves only through subtle distortions. Astronomers hunt for telltale gravitational microlensing events, where a rogue black hole's gravity briefly magnifies the light of a background star like a cosmic magnifying glass. In 2022, one such candidate made headlines when a team tracking star movements in the Milky Way noticed an invisible object roughly 7 times the mass of our Sun warping space-time around it. The culprit, likely a lone black hole drifting undetected just 5,000 light-years away. The real danger lies in their unpredictability. A close encounter with one of these wanderers wouldn't be a dramatic collision. It would be a slow, gravitational unraveling. As a rogue black hole passes through a star system, its tidal forces could stretch and compress planets, altering orbits over centuries. Jupiter's massive gravity already acts as our solar system's shield, deflecting comets and asteroids. Swap it for a black hole, and Earth's stable climate could be thrown into chaos. Entire planetary systems might be flung into the icy depths of interstellar space or hurled toward their host stars like cosmic billiard balls. Yet for all their destructive potential, rogue black holes might also be architects of cosmic oddities. Some astronomers speculate they could explain mysterious free-floating planets, worlds untethered to any star found drifting in interstellar space. A passing black hole's gravity might eject planets from their home systems, leaving them orphaned. Others suggest these wanderers could even seed new star formation, as their gravitational wake compresses nearby gas clouds, triggering stellar birth in their path. Destruction and creation intertwined once again. The most unsettling truth: there could be millions of them. Current estimates suggest the Milky Way alone might host anywhere from 10 million to 1 billion rogue black holes, relics of the galaxy's violent past. Each one is a testament to the chaos of stellar evolution, whether born in the collapse of massive stars or the mergers of binary black holes that received a gravitational kick strong enough to escape their birth clusters. And while the odds of one disrupting our solar system are vanishingly small, their existence is a reminder that the universe is far from orderly. The hunt for these invisible drifters is pushing astronomy to its limits. New projects like the Vera Rubin Observatory's Legacy Survey of Space and Time will scan the sky with unprecedented precision, potentially spotting microlensing events by the thousands. Meanwhile, pulsar timing arrays networks of ultra-precise cosmic clocks could detect the ripples in spacetime caused by a passing black hole's gravity. Every new detection peels back another layer of mystery, revealing a cosmos more dynamic and unpredictable than we ever imagined. Rogue black holes don't just challenge our detection methods, they defy our cosmic expectations. In a universe where we're used to celestial objects following orderly orbits, these wanderers are the ultimate rule breakers, moving to the silent rhythm of gravity's whim. They remind us that for all our maps and models, the cosmos still holds dark corners where the unknown lurks, waiting to rewrite the rules. Every second, trillions of invisible bullets rip through your body, cosmic rays from the darkest corners of the galaxy, pelting Earth with energies that dwarf anything our most powerful particle accelerators can produce. These aren't gentle wisps of starlight. They're atomic nuclei, mostly protons accelerated to nearly light speed by supernova shockwaves, black hole jets, and other violent cosmic engines. Some have traveled millions of years before slamming into our atmosphere, where they spark cascades of secondary particles in a silent fireworks show that never stops. What makes these galactic cosmic rays so fascinating isn't just their origin. It's their potential to shape life on Earth in ways we're only beginning to understand. When these high-energy particles collide with air molecules, they create air showers, avalanches of electrons, muons, and other particles that rain down to the surface. More intriguingly, they may seed low-altitude clouds by ionizing atmospheric molecules, which then attract water vapor like microscopic magnets. Satellite data has revealed curious correlations between cosmic ray flux and cloud cover, suggesting these far-traveled particles could be subtle players in Earth's climate system. The intensity of this particle bombardment isn't constant. Our solar system's journey through the Milky Way exposes us to varying cosmic ray densities as we pass through different galactic environments. When the Sun is active, its magnetic field strong, it acts like a cosmic umbrella deflecting many incoming particles. During solar minimums, that shield weakens, and cosmic ray penetration can increase by 20% or more. Even Earth's own magnetic field dances with these particles, funneling them toward the poles where they ignite the aurora's nature's version of a cosmic ray detector. Some of the most energetic cosmic rays carry mind-bending power. The "Oh my God" particle detected in 1991 hit the atmosphere with the kinetic energy of a baseball pitch, all concentrated into a single proton moving at 0.9999999999996 the speed of light. Tracing these ultra-high-energy cosmic rays back to their sources is like trying to find a specific grain of sand on a beach during a hurricane. Their paths get twisted by interstellar magnetic fields, leaving astronomers to piece together clues from their composition and energy spectrum. The real surprise: cosmic rays might have played a role in life's origins. Laboratory experiments show that when these particles strike simple atmospheric gases, they can produce amino acids, the building blocks of proteins. It's possible that over billions of years, this constant particle rain provided raw materials for early biochemistry. There's even evidence linking cosmic ray fluctuations to mutation rates in microorganisms, suggesting these galactic visitors could have subtly influenced evolution itself. Yet for all their creative potential, cosmic rays also pose challenges. They're a major concern for space travel, as astronauts outside Earth's protective magnetosphere receive doses equivalent to hundreds of chest X-rays per year. Future Mars missions will need innovative shielding, perhaps using water or plastics rich in hydrogen. to protect crews from this invisible hail. Even airline passengers at high altitudes receive marginally higher radiation exposure, a reminder that we're never truly separate from the cosmos. This constant particle bombardment connects us to events across the galaxy. When a star explodes 30,000 light-years away, some of its energy eventually reaches us in this form, not as light, but as atomic fragments carrying whispers of distant catastrophe. The iron nuclei in cosmic rays tell of supernova, while heavier elements hint at neutron star mergers. Each particle is a messenger, and we're only just learning to decode their stories. So the next time you feel a random shiver or notice an unexplained shift in the weather, remember, it might not just be Earth's atmosphere at work. The galaxy itself is reaching out, touching our world with invisible fingers, reminding us that we're part of a much larger system, one where even the tiniest particles can have outsized effects on planets, climates, and perhaps even the course of life itself. The universe isn't just expanding, it's accelerating, as if some invisible hand is pressing harder on the cosmic gas pedal with each passing moment. This mysterious force, dubbed dark energy, isn't just shaping the cosmos, it's rewriting its ultimate fate. Imagine a loaf of raisin bread baking in the oven where the raisins represent galaxies. At first, the dough expands evenly, carrying all raisins away from one another. But if the oven suddenly turned up its heat, the dough would stretch faster and faster until eventually the raisins couldn't even see each other across the growing voids. That's the reality dark energy is creating. A future where galaxies will vanish from one another's skies, not because they're moving, but because the space between them is stretching faster than light can bridge the gap. We've only known about dark energy for a quarter century, thanks to a cosmic bombshell dropped in 1998. Two teams of astronomers were measuring distant supernova, expecting to find the universe's expansion slowing under gravity's pull. Instead, they discovered the opposite. The explosions were fainter than expected, meaning space had stretched more than predicted since their light was emitted. The implication was staggering. Something was overpowering gravity on the largest scales, pushing galaxies apart at ever-increasing speeds. Later measurements of the cosmic microwave background and large-scale galaxy distributions confirmed it. Dark energy makes up about 68% of the universe's total energy budget, dwarfing both visible matter and even its enigmatic cousin, dark matter. What makes dark energy so unsettling isn't just its dominance, it's how little we understand it. The simplest explanation, proposed by Einstein himself, is the cosmological constant, a property of empty space itself that exerts negative pressure, causing expansion. Quantum physics suggests that even a vacuum should teem with particle-antiparticle pairs blinking in and out of existence, potentially contributing energy. But here's the problem. Calculations predict a vacuum energy density up to 120 orders of magnitude larger than observed, a discrepancy so vast it's been called physics' most embarrassing problem. Alternative theories suggest dark energy might not be constant at all, but a dynamic field evolving over time, like a fifth force of nature we've yet to fully grasp. The consequences of dark energy's reign are both grand and eerie. In about 150 billion years, every galaxy outside our local group will have receded beyond our observational horizon, their light stretched into undetectable infrared wavelengths. New stars will cease forming as galaxies exhaust their gas supplies, leaving the universe dominated by red dwarfs glowing faintly for trillions of years before sputtering out. Eventually, even black holes will evaporate via Hawking radiation, leaving behind a cold, empty void where nothing happens forever. This heat-death scenario, driven by relentless expansion, is the most likely endgame if dark energy remains unchallenged. Yet there are tantalizing hints that the story might be more complex. Some observations suggest dark energy's strength could vary slightly across space or time, challenging the cosmological constant model. If true, it opens wild possibilities. Perhaps dark energy could decay, reversing the acceleration or even flip sign, causing a catastrophic big rip where galaxies, stars, and even atoms are torn apart. Other theories propose that dark energy's effects could be an illusion, a byproduct of our three-dimensional universe existing on a higher dimensional brane in string theory's multiverse. The hunt for answers is driving next-generation projects like the Vera Rubin Observatory and the Euclid Space Telescope, which will map billions of galaxies to track expansion's history with unprecedented precision. By measuring how cosmic structures grow and light bends across vast distances, these missions could reveal whether dark energy is truly constant or something more exotic. The stakes couldn't be higher. The ultimate fate of everything, from galaxy clusters to the atoms in our bodies, hinges on the nature of this shadowy force. Dark energy doesn't just defy understanding, it humbles us. For all our cosmic maps and particle colliders, the universe's dominant component remains a mystery, its fingerprints visible only in the grandest scales of space and time. It's a reminder that the cosmos still holds cards close to its chest, and that the greatest discoveries might not lie in the stars we see, but in the invisible threads weaving the fabric of reality itself. Picture a clock ticking not for minutes or millennia, but for timescales so vast they make the age of the universe seem like the blink of an eye. This is the countdown to heat death, the universe's slow fade into eternal stillness. Unlike dramatic collapses or explosive endings, this cataclysm isn't marked by fire or ice, but by an unbreakable law of physics. Entropy, the cosmic tendency toward disorder, will eventually smooth out all energy differences until nothing can change anymore. No stars will burn, no particles will collide, no thoughts will form. Just an endless, uniform sea of near-absolute zero particles, too sparse and evenly distributed to fuel even the faintest flicker of activity. The roots of this chilling scenario trace back to the 19th century, when physicists first grappled with the implications of thermodynamics. The second law, that entropy in a closed system always increases, became a grim prophecy when applied to the cosmos. Every process, from nuclear fusion in stars to the electrical impulses in our brains, relies on energy gradients, hot to cold, high pressure to low, concentrated to dispersed. But given enough time, those gradients will vanish. Stars will exhaust their fuel, black holes will evaporate via Hawking radiation, and even the protons composing matter may decay into photons and leptons over incomprehensible timescales. The universe won't end with a bang or a crunch, but with a whisper, a final sigh as the last usable energy dissipates. Here's the twist: dark energy accelerates this fate. As the universe's expansion accelerates, galaxies, stars, and eventually atoms will be torn beyond causal contact. Imagine two fireflies in a rapidly inflating balloon, drifting apart faster than their light can reach one another. In 1 trillion years, civilizations, if any still exist, will see only darkness beyond their local group of galaxies. In 10 to the power of 100 years, a googol, even black holes' cosmic vaults that once trapped energy, will have radiated away their mass, leaving behind a dilute soup of photons and elementary particles so far apart they might as well be alone. Yet the heat-death scenario isn't just about absence, it's about transformation. The universe's energy won't disappear, it will simply become unusable, like a battery drained to perfect equilibrium. Some theories suggest quantum fluctuations might spark rare Boltzmann brains, momentary configurations of particles that briefly mimic consciousness in the void. Others propose cyclic universes or quantum resets, though these remain speculative. What's certain is that the cosmos we know, vibrant, dynamic, full of structure, is a fleeting phase in a much longer, quieter story. The irony, heat death is the ultimate democratizer. Whether a galaxy, a planet, or a single atom, all will share the same fate: isolation in a vast, unchanging expanse. It's a humbling reminder that even the mightiest cosmic forces bow to entropy's slow grind. And while this future lies so far ahead it defies imagination, it shapes how we understand time, existence, and the extraordinary privilege of living in an era when the universe still sings with light and motion. From the fiery birth of the cosmos in the Big Bang to the silent fade of heat death, these 32 cosmic cataclysms aren't just historical footnotes, they're the turning points in an epic still being written. Each collision, explosion, and gravitational dance left fingerprints on the universe we know today. The gold in your jewelry forged in neutron star mergers, the oxygen you breathe scattered by supernova, even the stability of Earth's climate shaped by our solar system's journey through the Milky Way's spiral arms. These events blur the line between destruction and creation, proving that chaos isn't just an end, it's often the first step toward something new. What's truly humbling is how deeply interconnected we are with these grand cosmic processes. The calcium in your bones was once stardust, the iron in your blood a relic of a dying star's last gasp. Our very existence hinges on a delicate chain of catastrophes, a moon-forming impact that stabilized Earth's tilt, asteroid strikes that wiped out dominant species to make room for mammals, even galactic mergers that enriched the Milky Way with fresh stellar material. The universe doesn't just host life, it sculpted the conditions for life through billions of years of violent, beautiful upheaval. Yet the story doesn't end here. Right now, new cataclysms are unfolding across the cosmos, Betelgeuse brewing a supernova, the Milky Way and Andromeda locked in a slow-motion collision, rogue black holes drifting unseen through the dark. Somewhere, a star's collapse is seeding space with the elements for future planets. Elsewhere, dark energy stretches the fabric of spacetime itself, quietly rewriting the universe's destiny. These aren't distant abstractions, they're reminders that we're not just observers of the cosmos, we're participants, riding a planet that's itself a traveler in this ever-changing galactic landscape. The greatest gift of studying these cosmic upheavals isn't just knowledge, it's perspective. They teach us that endings are often beginnings in disguise, that fragility and resilience are woven into the universe's fabric, and that even in a cosmos governed by colossal forces, there's room for wonder. So the next time you look up at the night sky, remember, you're not just seeing stars, you're glimpsing chapters in a story where catastrophe and creation dance together. A story that began with fire and will end in ice, but in between gave rise to a universe capable of looking back at itself and marveling at how far it's come. The echoes of these cataclysms aren't just shaping galaxies and stars, they're inviting us to understand our place in a saga billions of years in the making, with countless twists still to